Welcome. Today we will be taking a look at the notes worksheet entitled Hyperbolas Day 3. It's time for us to just tie up some loose ends on the hyperbolas and the conic sections in general, so we'll do exactly that piece. Why don't we go ahead and start out with just a review problem here, example 1, and just have a nice equation here in standard form. Let's find all the characteristics that go with it, and what do you say we do a nice little sketch along the way too. So it says determine the center, vertices, foci. We'll probably do the endpoints on that conjugate axis too. And there's the equation. And I guess it's all going to stem from the center, so let's go ahead and write that down and start that process, and let's get our h and k. We will focus in on h and k throughout this lesson. And let's see, I'm looking at a -4 and a 3 as h and k there. Hope you are as well. And so let's go ahead and find -4, 3, 1, 2, 3, 4, 1, 2, 3, and let's just put a little x right there. That should suffice. Okay, now everything is going to come off of there, so let's be careful about a couple things. I've been just trying to be as consistent as possible, starting with the vertices. I think about my a value, of course, and remember a is always out in front with the direction there, so a is going to be 2, and we're going to be going left and right from the center there in order to get our vertices. So I'm going to go ahead and write all that down, of course, and hope that makes sense. Again, the numbers down here don't tell us the direction. It's the variable out in front for the hyperbola. Okay, so let's go ahead and let's see if we can do this without plotting them. So kind of talk about the mathematics that we've accomplished so far. What we basically said is if we move left and right on the coordinate plane, it's the x-coordinate that's going to change. And so it's going to change by 2. Let's go ahead and subtract 2. I should get -6, 3. And what do you say we add 2? And that would be -2, 3. So just left and right on the coordinate plane. And then again, if you can't pull that off, no problems at all. What you want to do is just count 2 units to the left, 2 units to the right there, and then should be able to kind of see that piece. All right, very nice. Let's go ahead and do the endpoints on that conjugate axis. Again, excuse my poor shorthand for it. But as soon as you think about that, immediately you're associating it with b, and I'm getting a b value of 4 there, by the way. Sounds good, and obviously the opposite direction. So everyone on your paper, if you could write up and down, that would be ideal. And you could see that obviously under the y right there, so that's great. And let's go ahead and see if we can write out those ordered pairs for those endpoints. And just refreshing memories here, if I'm moving up and down on the coordinate plane, I'm changing the y value. In this case, I'm adding 4 and subtracting 4. So it looks like the x value stays the same. Add 4 to that. Looks like I'm getting -4 and 7. And then also subtract 4 from it. And 3 minus 4 would give me the -1. So hoping that makes sense, just going up and down. Again, if you have any issues with that, then just count it out and then figure out the ordered pair from there. So 1, 2, 3, 4, and just a little x right there. 1, 2, 3, 4. How about a little x right down there? And my rectangle is ready to go. Let's get that in place. Should look pretty good. Nice. And we'll be talking about our asymptotes here today during the lesson. So what do you say we go ahead and sketch those in? And there we go. It's all looking pretty nice. All right, so I have those pieces. Usually I sketch at this stage, but why don't we go ahead and do foci first? And so we are going to need a little mathematical help on this one. I'm going to go ahead and have to do my c squared, a squared, and b squared equation. And if you remember, of course, with the hyperbola, it's a squared plus b squared. So just make sure you orient that correctly, especially compared to the ellipse where it is slightly different. So that's the biggest thing I think in this whole unit is distinguishing all the information between a hyperbola compared to an ellipse. So in this case, I think we've got this going nicely. And I think we've seen these numbers before. The nice thing about that standard form equation, it's pretty easy to use, especially with a, b, and c, because a squared and b squared are given. And again, it looks like I'll get c squared equals 20. C is equal to the square root of 20. I'm getting a 2 root 5 on that if I pull that off appropriately. And same deal, guys. Of course, once I have my 2 root 5, let's go left and right on that. And when I go left and right, Of course, we all know that the x-coordinate does change. And so hopefully all this information on the board is making pretty good sense at this stage. Let's go ahead and place those foci accordingly. Remember, coming off the center, that's the key. Always come off the center. And so I would do something like this, x changing by 2 root 5 going to the right, something like that. And sorry about that, so negative 4 and then minus 2 root 5 and then comma 3. Oops, let me make sure I've got that right for you. There we go. So 2 root 5 and then comma 3. Nice. If you wanted to consolidate this, I think we've spoken about that before. You're more than welcome to, of course. So root 20 is in between 4 and 5 units there, so I'll go ahead and just count it out as best I can. 1, 2, 3, 4, and then probably somewhere right in there. Same thing, 1, 2, 3, 4, and then somewhere maybe right in there, give or take. Sounds great. I think we're ready for our sketch. Hope you are as well. And I'm going to go ahead and put that in just kind of like that. So remember that the arms on the hyperbola branches go towards these asymptotes. And so let's go ahead and put those in place. And so those asymptotes act as boundaries for our curves, and that's looking pretty good. Okay. So a nice little review problem. Hopefully, again, all that information is coming together nicely for you. Center, vertices, endpoints on the conjugate, foci, and then from there, obviously, we're able to kind of view it on the coordinate plane pretty nicely. All right, perfect. Well, let's get into one more algebraic piece. We did kind of talk about this on the previous lesson, dealing with the equations for asymptotes when the center was at 0, 0, and it was pretty straightforward, all things considered. But now what we want to go ahead and do is start to translate those asymptotes off having them meet at the center, which would be the origin. So in this case, now the center is going to be h and k, I guess, long story short there. And so there are a couple ways to go ahead and do this. I'm just going to try to streamline it a little bit for you. And we're going to use the idea of a transformation, essentially, what we would call a shift. And so that's what I have right here. If you can kind of highlight that piece on your paper, that would be ideal. But essentially, what we've been doing all along with these conic sections is we've been starting with the main point at the origin, and then we've been shifting it off the origin, either left or right or up or down, and kind of going from there. And that's how we've kind of been dealing with just sort of an x and then an x minus h, or a y and a y minus k. So long story short, when I replace all my x's with x minus h, what that does, and we've seen this before with transformations, it represents basically a horizontal shift of the graph. And if everything shifts, then the center for our asymptotes also shift as well. And then changing all the y's to y minus k, what that essentially does is it represents what we would call a vertical shift on the graph. And that's basically all we're doing. Instead of 0, 0, we're going to go ahead and shift it to a center being at h and k. And all that means is we're going to replace our x with x minus h, and we're going to replace our y with y minus k. It's going to be pretty straightforward. So let's go ahead and do a quick review of yesterday's lesson where the center was at 0, 0. And so if you remember, there were two scenarios right there. Why don't we just write the words horizontal and vertical? I think that's probably the best course of action. So this part you're going to have to kind of remember, but with the horizontal one, remember just y equals mx plus b. We have two asymptotes. If you remember, one was the plus and one was the minus. And I guess I would ask you this of basically, which is it for the slope? Is it a over b, or is it b over a if it's going horizontal? And if it is a horizontal hyperbola, then as we hopefully remember, it's b over a. Okay, very nice. Now the vertical piece then, if you remember, was just this, plus or minus. And because we're going vertical to the vertices, that's the rise part, as we kind of talked about on the previous lesson, then it was that right there. And so here's the beauty of this, trying to make a long story short for you, if I possibly can. Basically, if I want to go ahead and shift the equations of the asymptotes off of the origin, essentially, where they have intersected before, either here or here, all I have to do is perform the shifts. Vertical shift would be replacing y with y minus k. Horizontal shift would basically be replacing x with x minus h. And so here we go one last time, and actually I guess put an asterisk next to this one. What are the equations of the asymptotes if the center is at h and k? Well, guys, here's how it's going to play out. I replace the y with y minus k. That'll shift it vertically. And by the way, let's put horizontal above this before I do forget. Plus or minus b over a. And then instead of x, well, very simply, we're going to shift it x minus h. Nice. So it's going to be either h units to the right or h units to the left. That right there, by replacing that value with x minus h, will accommodate exactly that piece. Okay, and then let's go ahead and do the vertical. Very, very similar in nature. So vertical, again, instead of y, it's y minus k. Vertical is just switching the slope. Rise over run would be a over b. And again, instead of times x like it was up here, hey guys, we just go ahead and replace x with x minus h. I will ask us to kind of work with that a little bit. There's just some, I think, some decent math working with lines that we need to sort of deal with. So I'll ask us to kind of work with this and then do some simplifying from there. But really shouldn't be anything over our heads. Well, let's go ahead and put this in place. So obviously, anytime I introduce a concept or an idea or whatever the case may be, we do need to do an example to kind of back it up and reinforce it and see it with some numerical values. So first course of action, everybody, it says determine the equations for those asymptotes. So if that hyperbola is defined by this equation right here, and I think what we're going to have to do is figure out which direction it goes, and then let's think about A and B, and then watch how easy this is going to be. So first and foremost, everyone, is this a horizontal hyperbola or is it a vertical hyperbola? And if you look out in front, it looks horizontal. So I'm going to write that right up here. Just good things to put mentally in place. And then probably start needing to talk about A and B in one way or another. And I hope you're in agreement that A is going to be the 2 and B is going to be the 3. So A and B. Okay, very nice. Now, I guess here's the idea. Let's go ahead and maybe get just the generic template of this. And if it's a horizontal one, as we just saw above, it's y minus k. It is the horizontal one, so here's where you're going to have to be careful, and it's probably the only thing you're really going to be being careful with, is it's going to be b over a in terms of the slope, and then x minus h. Well, guys, here's the beauty of it. Within the equation, we have all of that stuff, and so it's just a matter of putting it together. We've done h and k when we talked about the center of the hyperbola. Well, it's also where the two asymptotes intersect. And so those values stay consistent when we do the equations of the asymptotes. So nice and easy. How about this? Y plus 3. So there's my y minus negative 3. And then plus or minus, what do you say we do a 3 over 2 here for b over a? And instead of x, we shifted it 2 units to the right. And that's exactly what happens when we work with these hyperbolas. We shifted it 2 units to the right. And so I just replaced my x with x minus 2 to move it 2 units to the right. Now, theoretically, this is it. These are your equations of the asymptotes. Isn't it pretty straightforward? I would love for us to go ahead and take one step further there and see it as 2 separate lines in y equals mx plus b. Sorry about that, but I would ask you to do that if that's all right. So here's what I'm thinking. Let's go ahead and just do 2 branches kind of off to the side right here, and basically 2 different equations. It's y plus 3, and there's the positive 3 halves, x minus 2. And then, again, just the way it's written there, kind of breaking it apart, it would be, let me just make sure I have that as a y plus 3. So y plus 3, and then that negative 3 halves. And what did I say there? X minus 2. So those would be really the 2 equations kind of separating them out. And you know, you've been doing y equals mx plus b now for at least a few years. I would just ask us to go ahead and put that together on this. So as I said before, I'll apologize for that, but would like to see it in action regardless. So let's go ahead and distribute. So I would do 3/2 x, and then it looks like when I go ahead and do that piece right there, 3/2 times 2 looks to be a -3 there. So I hope everyone's okay with that, distributing that in, and looks like I would get that piece. And then once we distribute, not too bad, I think we'll go ahead and just get it into y equals mx plus b. What do you say you bring that 3 on over to the other side? And here it is. One of the equations would be y equals 3/2 x minus 6. I like that. That's great. I would encourage us to do it one more time here. And so let's go ahead and pull this off. I would say distribute the negative 3/2 in, so negative 3/2 x. And in this particular case, I'll do the same thing. How does a plus 3 sound as a result, though? So negative 3/2 times negative 2. Those 2's would cancel, and you should get a 3 right there, negative times negative being positive. Perfect. I just have one easy step here. Just subtract that 3 on over to both sides, and I end up getting y equals negative 3/2 x. I just happen to like this expression a little better. So if you don't mind, on just a few examples that I give you that kind of look like this, if you could go ahead and put that in y equals mx plus b, that would be great. I'm going to bring my graphing calculator up just to see it in action, if you don't mind. You can just sit tight for a moment. That would be great. And I wouldn't mind just kind of seeing this in action a little. So let's see, 3/2 x minus 6, and then negative 3/2 x. And I'm going to just go ahead and hit zoom in number 6. And if you notice, take a look, two lines on the coordinate plane. Look at where they intersect, everybody. Do they intersect at the center of the hyperbola, which would be at 2, negative 3? And if you kind of look at that right there, seem to be. And you can envision the hyperbolas, if we were to kind of put that in, that would look great. So I like that piece. When you put it in y equals mx plus b, and again, kind of looking at that graphically right there, you see it really fits everything we've talked about. And that's sort of the best piece, seeing all the connections. All right, very nice. Let's move on to my next board there. So again, we just tied up some loose ends on the asymptotes. Hopefully that's all right for you. And then just one more piece, not too bad. Won't hold you too accountable for this, but some interesting things that we can kind of quickly take a look at here. So eccentricity, coming back, we talked about eccentricity of an ellipse, and here's the eccentricity of a hyperbola. So let's fill in a couple blanks and go for it. The eccentricity of a hyperbola is mathematically defined as, and it does say just like the ellipse, so good little review. And do you remember? C over A. One of the easier calculations we've done in this unit, just C over A, and kind of nice. If you remember, on the ellipse, the interval for the eccentricity was between 0 and 1. I'm just going to write that here. You don't have to if you don't want to. But the ellipse, the eccentricity was anywhere in between 0 and 1. And that was because C was smaller than A. So when you take a smaller number divided by a larger number, you get a number between 0 and 1. Well, guys, I would ask you this. What do you think the interval is for the eccentricity of a hyperbola based on what you know about C and A, and if you were to have to divide those? Well, what's interesting, again, making the distinction between a hyperbola and an ellipse, in a hyperbola, C is actually larger than A. So the foci are further away from the center than the vertices are. So C is larger than A, so you're going to have a larger number over a smaller number, and I'm hoping that you thought of this, greater than 1. Now, what we're just going to take a look at is what happens as the eccentricity gets larger and larger and larger. So, when we start just past 1, as it increases, it gets larger. What do you think happens to the branches of the hyperbola? Do you think that they get wider, or do you think they get narrower? So what do you think? Totally a 50-50 guess. I wouldn't necessarily expect you to have a really, a definitive opinion on this. It's just basically, I'll put this in and then we'll find out. So take a little guess there. What do you think? As the eccentricity increases, do you think those branches are going to get narrower, or do you think they're going to get wider? I've got my Sketchpad program up, and I'll go ahead and boot that up in just a second. We'll go ahead and check it out. Okay, well hopefully you put in something there. And so let's go to my window, and there it is, all on eccentricity. Now, this program is defining eccentricity in a slightly different way. By the way, just one thing to note here, look at the intervals. So between 0 and 1 is the ellipse. When the eccentricity is 1, it's actually a parabola. I'll show that to you momentarily. And then if it's bigger than 1, and then obviously it's a hyperbola. Okay. Well, guys, I'm going to go ahead and do what's called sweeping E. So here it is right here in between 0 and 1. That's why, as it says, look at that screen. It says it's an ellipse. So watch what happens. And keep an eye as it gets larger and larger. Are the branches getting wider or narrower? So there it is, there it is, there it is. Now we go hyperbola. Ah, look at that. As the eccentricity increases, look how wide those branches are getting. And as it comes back in, it looks like they're getting narrower and then turning back into the ellipse. Nice. Let's see it sweep out one more time. Go, go, go. Cool. And so the answer was wider, as a matter of fact. As the eccentricity gets larger and larger, the branches of the hyperbola, they get wider and wider. Watch this, one more thing just real quick. Keep an eye right here, and let's see if you can spot it. As it hits 1, this word should change to parabola just momentarily. Did you catch it? So as it hits 1, watch this. It's going to change to a parabola. You can barely see it. Don't blink. Ready? Here it comes. Here it comes. Did you catch it? So when the eccentricity is 1, it actually forms a perfect parabola. Pretty cool. All right, so we've got an answer. Might as well go ahead and put that in place. And it looks like as the eccentricity increases, it actually does get wider. Kind of cool. All right, great. So just not too bad there, just dealing with one of the measurements, dealing with hyperbolas like we saw before. Now, last piece, everybody, if you would. We've been talking now with 4 conic sections, 4 different general equations, all very, very, very similar in nature. And as I've said before, just the minor modifications on the equation change the geometry on the coordinate plane. And so here I have 8 general forms of a conic section equation. And basically I'll let you know it's 2 of each, 2 circles, 2 ellipses, 2 parabolas, 2 hyperbolas. And I want to know, without doing a whole bunch of completing a square, I want to minimize the math if possible. What I want to know is which is which. So how are we going to figure it out? Well, here's what I'm going to do. I'm going to write a little just down below here if you want to write some things in. If you figure this out pretty easily, then don't sweat it. But I would argue, out of the 4, there is one that is quite a bit different than the other 3. In terms of the general form now, you have it all under your belt in terms of the experience. One is different than the other 3. And which one is that? Well, I would argue that it is the parabola. And so I would look for the parabola first, just me. Because what do we know about the parabola equation compared to the other 3? Well, it's the one that only has one variable squared. All the others, if you remember, have an x squared and a y squared. So parabola, I'm going to write that again. If you don't want to, don't worry about it. Only one variable squared. So I think it's the easiest one to locate right away. And so let's see. How about B? It's the y squared, and the x is just linear. So B has to be a parabola. All right, which is a parabola? I said 2 of each. I've got to find them. Oh, there it is. Down at F. Everyone see that? Here the x is squared, but the y is only linear. So F is also the parabola. Oh, that is great. So again, just in my opinion, and that's all it is that's the easiest one to locate. All right, now we've got circles, ellipses, and hyperbolas left. So I guess I would ask you, which do you think has the greater distinction amongst the 3? And which would it be? Which would you find next? Well, for me personally, I would probably look for the hyperbola next. And what's the difference between a hyperbola and the other two? Well, as we've kind of have seen before, the hyperbola is the one where one squared variable is negative. So that's what I would look for. X squared and y squared, one is positive and one is negative. So let me write that in. One squared variable is negative. And we kind of talked a lot about that with the equations. So, as I'm kind of looking at them, it's just this piece right here. Just that alone would change it from whatever the other conic sections are to a hyperbola. That minus right there is what makes it a hyperbola. And let's see, where is that other one? Can't seem to locate. Oh, I guess there it is right there. So this and this, C and E. So hyperbola here, and I guess it was hyperbola here. Does that make sense? So just in this case, one of the variables is squared. I'm sorry, one squared variable is negative. Let me say it that way. All right, let's go get the last two. Now circles versus ellipses. Now I gave a really, what I said, a pretty poor definition of what an ellipse is, but I think it works for the most part. I sort of called an ellipse a stretched circle. And what stretches the circle in the equation is it's the numbers in front of the squares. If the numbers in front of the squares are the same, then it's perfectly balanced. It's not stretched in one direction of the other or the other. But if I have an unbalancing in terms of the numbers in front of the squares, then it stretches that circle in one direction or the other and forms an ellipse. So I would say find the ellipse where the coefficients in the squares are unbalanced. So coefficients of squared terms are unbalanced. And so in this case, kind of looking at this, letter D, I think I highlighted before, that has to be the case. If we saw it in standard form, we would know exactly which direction it's stretched, so to speak. And then I guess the last one there I'm seeing is G. That's also the ellipse. And so both positive, but unbalanced in terms of those two numbers right there. Whereas, of course, the circle would be perfectly balanced with those two coefficients. Most of the time you see it as just x squared, y squared. I wrote that this is a tricky one because theoretically I can just divide this whole equation by 2 and I would still get my x squared and y squared. So that last one is also a circle. So circle is kind of the last one, at least that I look at, and basically coefficients are the same. So coefficients of squared terms are the same, and they both have to be positive, of course. So let's see, coefficients of squared terms are the same. And I guess for each of these, let's go ahead and just put both positive. I think you knew that to be the case, but I'm just trying to cover my bases, of course, up there. So both positive would be the case. And so, of course, top one, circle. Bottom one, circle. And we've got our winners, 8 for 8. That is awesome. So again, it's just kind of fascinating seeing these algebraic equations in action, where, as I said, very slight changes in the equation really just dramatically change the geometry on the coordinate plane. And that's what we've been exploring all through this unit. Some great stuff. All right, why don't we kind of wrap it up here at this stage, and you just let me know if you have questions along the way. But we've done, let's see, at this stage, 1 circle notes worksheet, 3 ellipse notes worksheets, 3 parabola notes worksheets, and 3 hyperbola notes worksheets. A lot of information. Putting it all together is always the big test in this unit. And obviously, guys, you just let me know how I can best support that. Well, thanks for listening, of course. Try getting some practice on this stuff, and help each other out and ask questions and all the stuff to be successful. Thanks.